Today, let me guide you into a region of the cosmos where science hesitates, myths whisper, and reality shows cracks we were never meant to see. The cosmic cold spot. What created this enormous frozen patch? Why does light lose energy as it passes through it? And what kind of cosmic event could leave a mark across nearly 1 billion light-years of space? As we step into this region of the sky, we're here to uncover what it's hiding. This is the place where our understanding ends and the mysteries begin. Across the ancient cosmic microwave background, the faint radiation left behind by the Big Bang, scientists discovered a region that behaves like a flaw in reality. This region is known as the cosmic cold spot, a colossal patch of sky so unusually cold and so impossibly empty that even the standard model of cosmology struggles to explain it. The cold spot spans almost 1.8 billion light-years, making it one of the largest anomalies ever recorded in the observable universe. In theory, the early universe should have been nearly uniform, with temperature variations so small they barely matter. Yet the cold spot is drastically different. When NASA's WMAP satellite first detected it in 2004, researchers assumed the data must be corrupted. But when the European Space Agency's Planck mission later confirmed the same chilling imprint with higher precision, the scientific community realized the anomaly was disturbingly real. Why does this matter? Because statistical models say the odds of such a temperature depression occurring naturally are incredibly tiny. It is like predicting an ocean to be the same temperature everywhere, except for a single region the size of a continent that suddenly freezes without reason. Something unusual must have shaped this part of the cosmos. One explanation is the existence of a supervoid, a massive region containing significantly fewer galaxies than average. Light passing through a supervoid can lose energy, making the region appear colder. But here's the problem. Even the largest known supervoids cannot produce the extreme temperature dip seen in the cold spot. To match the observations, the void would need to be hundreds of times larger than anything the universe normally forms. This puzzle led to one of the boldest ideas in modern cosmology. Some physicists proposed that the cold spot may be a bruise from a collision with another universe. If a parallel universe brushed against ours shortly after the Big Bang, its gravitational imprint could distort the temperature of the cosmic background, leaving behind a massive cold blemish. Remarkably, the cold spot's shape aligns with predictions from certain multiverse models. Surprisingly, ancient mythologies mirror the concept in poetic ways. Australian Aboriginal traditions describe a dark sky hollow where creation once touched another realm. Hindu cosmology speaks of countless lukas, parallel worlds separated by delicate boundaries. Though symbolic, these myths echo the idea that our universe might not be alone. Rarely discussed is another possibility. The cold spot may indicate an unknown physical process, one that challenges current cosmological principles. It suggests the universe might contain structures or forces humanity has not yet identified. Whether it's a supervoid, an interuniversal scar, or evidence of undiscovered physics, the cosmic cold spot stands as one of the most mysterious features in the sky, an enormous question mark imprinted on the universe itself.
Clear, steady, and scientifically authoritative narration with smooth, confident pacing, rooted in calm precision, yet carrying a subtle human warmth and rising curiosity whenever a new cosmic discovery unfolds, blending neutral clarity with a gentle sense of wonder that draws listeners into the thrill of exploration. If the cosmic cold spot were simply a rare temperature fluctuation, the story would have ended years ago, but the more astronomers investigated it, the stranger it became. the region does not merely appear cold, it behaves as if some unknown influence reshaped the fabric of space itself. When cosmic microwave background radiation passes through the area, the photon energy drops more than expected, suggesting that the cold spot once experienced an event powerful enough to alter the geometry of space-time. One idea proposes that the region might be a relic from the earliest fractions of a second after the Big Bang. During cosmic inflation, the universe expanded faster than the speed of light. If inflation did not occur uniformly, a pocket of slower expansion could have produced a vast underdense area. That pocket may now be what we call the cold spot. But this raises an uncomfortable question. Why would inflation falter in only one specific region? There is no known mechanism that selectively slows the expansion of one cosmic patch, while leaving the rest unaffected. The anomaly deepened when astronomers mapped galaxy distribution around the cold spot. Instead of finding a single enormous void, they discovered multiple layered underdensities, like nested hollows carved into the cosmic web. These structures appear arranged in a pattern that defies random formation. Some astrophysicists argue that such layering might be evidence of gravitational interference from something beyond the visible universe. This idea strengthens the multiverse collision hypothesis. According to certain inflationary models, universes form as bubbles within a larger cosmic landscape. When two bubbles collide, the boundary imprint can survive for billions of years. The cold spot's asymmetrical temperature gradient resembles the simulated outcome of such a collision. If this interpretation is correct, the cold spot could represent the first physical evidence that reality extends far beyond our cosmic horizon. Mythologies around the world also contain surprising parallels. The ancient Persian Bundishan describes a wound in the sky created when two worlds collided in primordial time. The Navajo speak of the dark earth door, a region of the heavens through which foreign spirits once entered. Even Norse cosmology references Gunangia, a vast cold void at the edge of creation where two realms met before forming the known universe. These myths, though not scientific, reflect humanity's age-old fascination with cosmic boundaries and the idea of interacting worlds. Modern surveys using radio telescopes revealed another peculiar detail. The polarization of radiation passing through the cold spot shows a subtle twist. This twisting pattern is faint yet statistically significant, hinting that the region may contain exotic forms of energy or curvature. Some researchers suspect the presence of cosmic textures, hypothetical defects formed during symmetry-breaking transitions in the early universe. These textures behave like knots in spacetime, pulling matter and light in unusual ways. If a cosmic texture exists within the cold spot, it could explain the localized distortion without requiring a multiverse. But textures are still theoretical, and no direct evidence has ever confirmed one. Even so, the cold spot remains their strongest candidate. Another rare possibility involves quintessence, a proposed dynamic form of dark energy that can vary in strength and direction. If quintessence once behaved differently in this region, it could have sculpted a large-scale depression in density. But current observations show no clear pattern of varying dark energy elsewhere, making this explanation speculative. Scientific curiosity continues to rise because the cold spot does not neatly match any single prediction. It sits at the intersection of cosmology, particle physics, and philosophy, challenging the assumption that our universe is smooth and isotropic. Instead, it suggests a cosmos marked by scars, memories, and deep anomalies, remnants of ancient processes we have yet to understand. Whatever the true cause, the cosmic cold spot stands as a reminder that even with all our telescopes and measurements,
the universe still hides phenomena powerful enough to rewrite our understanding of reality. As deeper observations continued, the cosmic cold spot transformed from a puzzling anomaly into a laboratory of unanswered questions. One of the most surprising findings came from gravitational lensing analysis. Normally, regions with less matter bend light weakly, but the cold spot shows a lensing pattern that does not fully match its visible matter distribution. Light passing through it bends in a subtle, inconsistent way, almost as if the underlying gravitational field shifts between layers. This irregularity hints that something more than empty space may be shaping the region. To investigate further, astronomers used high-frequency microwave instruments to analyze how photons lose energy inside the cold spot. They discovered a specific decline pattern known as the integrated Sachs-Wolf effect, but with an unexpected twist. The drop in energy is sharper than what classical models predict. This suggests that the cold spot may involve a non-linear interaction between cosmic expansion and large-scale structure formation, an interaction that standard cosmology has not fully accounted for. One emerging possibility is that the cold spot formed due to anisotropic expansion in the early universe. If a particular direction experienced slightly different expansion rates, it could leave behind a massive imprint. While inflation is believed to smooth out such variations, some quantum-level deviations may have survived. These residual imprints could later be magnified across billions of light years, forming regions like the cold spot that break the expected symmetry of the cosmos. Another compelling theory involves primordial magnetic fields. The early universe may have contained magnetic structures that evolved irregularly across cosmic scales. If a large-scale magnetic field collapsed or weakened unevenly, it might have produced a zone of suppressed temperature and reduced galaxy formation. This would align with the layered underdensities already observed. However, mapping ancient magnetic fields is nearly impossible, making the idea attractive but extremely challenging to test. A more exotic hypothesis suggests that the cold spot might be a region where dark matter properties differ from the surrounding cosmos. If dark matter is not perfectly uniform, but exists in multiple states, a patch with weaker clustering ability could form a vast underdense area. This fits with simulations showing that variations in dark matter's self-interaction strength can produce large-scale cosmic hollows. Yet detecting such variations requires technology far beyond our current instruments. Recent computational models introduce another fascinating angle. The cold spot may be an indication of a topological defect in space-time. During the universe's earliest microseconds, various symmetry transitions occurred, similar to phase changes in materials. If one such transition left behind a remnant irregularity, a fold, a twist, or a discontinuity, it could influence cosmic microwave background radiation billions of years later. These defects are known as domain walls or textures, and although never directly observed, they remain mathematically plausible. What makes the cold spot especially intriguing is its consistency. Over 20 years, across multiple satellites, instruments, and calibration methods, the anomaly has not shifted or weakened. Every new dataset reinforces the same conclusion. This region is not an observational accident. It is a fundamental feature of our universe, waiting to be decoded. Even more striking is that the cold spot may not be alone. Preliminary maps reveal smaller, less pronounced cold anomalies scattered across the sky.
If these patterns share a common cause, they could collectively point toward a deeper cosmological mechanism, one that shapes the universe at scales far beyond current understanding. The ending question therefore becomes unavoidable. Is the cosmic cold spot an isolated glitch in cosmic history, or the first clue to a set of hidden rules governing our universe? If future telescopes, like the Square Kilometer Array or next-generation CMB observatories, detect similar signatures, we may finally uncover whether the cold spot represents a rare accident, a structural feature of space-time, or the footprint of an unknown cosmic force. For now, one thing is certain. The cosmic cold spot stands as a reminder that even after mapping galaxies and decoding cosmic radiation, the universe still holds regions that behave like encrypted messages, signals written across billions of light years, urging us to question everything we think we know about reality.